So for this problem, what is happening here? So we want specifying that this is an AC circuit, and they want us to solve for the mesh currents. So here we're not really looking for anything particular, but they just want us to find the mesh current in the respective loops there. So how do we find the mesh current? So the first step, just like before, is to transform the circuit from the time domain to the frequency domain. That will involve changing all these passive elements, the inductor there, and then we have the capacitor here, another inductor there, changing these from what they are currently to their corresponding impedance values. And then the voltage source that is present here, we will have to present it in terms of its phasor form. So in this case, we'll start with the voltage source. Currently, it's given as a sinusoidal waveform. And here we have 100 cosine, and then we have 1000 t. If we just have 1000 t, we don't have an independent variable without a t. It implies that what we have there is a 0. Meaning, now the phasor voltage corresponding with this source, this has a subscript s, so I'll still keep it like that. It will store the peak voltage there, which is going to be 100 volts, and the phase angle which comes this side. In this case, the phase angle is 0 degrees. Basically, this is just 100 volts as the supplied voltage, I mean. After converting the voltage to phasor, now we can focus on the two inductors. Let's say for the first one, we'll get Z1. For the second one, we'll get Z2. And for the capacitor, we'll get Z3. So let's get Z1. Being an inductor, we know to say this is obtained by this formula. In this case, the angular frequency comes from the source present. In this case, that's 1000 rads per second. Then the inductance, in this case, 0.1. Both inductors are rated 0.1. So in this case, we end up with J with 100 ohms here. In the same way, Z2 for the second inductor. So for the second inductor, still going to have the same shape. Still J, the angular frequency, still 1000. And even here, the inductance is 2.1, as you can see here. So based on that, so yeah, that is 0.1. Based on that, when we simplify, it reduces to the same impedance. So we're done sorting out the inductors. Let's look at the capacitor. The capacitor, we know it's 1 over J omega C, which is 1 over J. What is our omega? Still 1000. What is our C? The capacitance. Capacitance here is 5 microfarads. So 5 microfarads interprets to 5 by 10 to the minus 6 there as our expression. So now we just have to simplify this expression. So here when we simplify, we get minus 200 with the J there. Okay. So we now have the corresponding impedance expressions or values. So meaning we can now redraw our circuit by only presenting the impedance and the phasor voltage here. Okay, so that is out. Let's include them now. So the phasor voltage, we saw that was 100. The phase angle was 0 degrees. And then finally, we go to the other elements. this inductor here, we so to say they both had J100 here. This one had minus J200. And finally, this had J100. Okay. Now that we have completed or transformed completely to the frequency domain, we can start looping around. So let's start with the first mesh. What do we have? Here, depending on how you want to approach it, you can take it. Which one is our one? So this is our mesh one. So we can say that we find this source, supply source, which is just 100 here. Then the two resistors present. So I can say the J100 will come first, which is this one here. Then finally we'll have this one, but this one is shared. This one is shared, so we'll add it plus J100. Oh, don't forget, you have to multiply by the current passing through. Currently, this is just resistance. We're using Kirchhoff's voltage law here. So it's resistance times the current passing through. So here, of course, we want to use the steady state current I1. Instead, this will be the phasor current I1. And here, won't use the sinusoidal waveform I2. Instead, we use the corresponding phasor current I2. Based on that, for this loop, we'll be multiplying by phasor I1. Here, since it's this second one down here, it's affected by I1 and I2. So here, we're going to say it's going to be I1 positive minus I2. You can look at it like this, but the one I like, which is faster, or which is easier for students to follow, is since it is part of this loop, we'll add it first with the loop. So plus, okay, so I've already done the plus here, meaning it will multiply I1. Then since it is shared with I2, now we'll subtract the same thing. But when subtracting it, now we'll multiply it with the one we are sharing with, which is I2. It is the last one in this loop, so this has to be equals to 0. Okay, yes, this one doesn't have a complex part. That's just a normal resistor. So this shared one doesn't have the complex part. It's not shared. So we can remove that part since that is just real. So yes, this is how it is going to look like. So from here, we just have to simplify this. The 100 can go to the right. So that now we have with the 100 I1 stem, then plus, now for this part, we have 100 here, I1, then minus 100 here, I2 is equals to, this 100 went to the right and became positive. So here now we can group the like terms, the terms with I together, the terms without I, or with the terms with I1 together, the terms with I2 together. These two here have I1, so I'll group them and factor out I1. When I factor out I1, this will remain as just 100. This will be 100J. So basically, I'll start with the real part 100 plus J100. And here we have factored out I1. Then next, only this term will be left. And for that term, it comes with minus 100 I2. Each term here has 100, meaning we can divide through by 100. So I hope you guys are seeing that. So I hope you're seeing that. When you divide by 100, you only have 1 here. J will remain alone here. I1 plus, now that's minus. Here as well, the 100 will go is equals to 1. So we can keep this as equation 1. With this done, we now do the same thing for the second loop. The second loop is this one here. And what do we see? Here, this loop consists of 1, 2, 3 circuit elements. So we can add them with the circuit itself. So here, the mesh current responsible is I2. So I'll say the 100 here, multiplying I2, I'll have the 100 with the I2. Next, the minus J200, multiplying I2 as well. So it's plus, but it comes with its own minus there. Multiplying I2. Then we move on to the next one. This one here, also affected by I2, so we have plus J100 multiplying I2. But this one here was shared. We added it, now we'll subtract it. But in subtracting it, we'll multiply it by the mesh current it was shared with, which is I1. So it would be multiplying I1. That was the last one, so equals to 0. From there, we now just have to simplify. So simplifying this, what do we have? So this is 100 I2 minus J200 I2 plus J100 I2 minus 100 I1. Only one term here has I1, so I want I1 to be first. But these two both have J, and here every term here has 100 again, so I can divide by 100. So you have I2 minus J2 I2 plus JI2. Then here we have I1. These two simplify. We now have I2 here. This is now minus JI2 is equals to 0. These two both have I2. We can factor out I2. So now we only have 1 minus J, and I2 comes out is equals to 0. So this is now what we have here. Any questions? Okay. Now, how do you solve these expressions? So in most cases, you can try to use Cramer's rule. But if you're not, usually Cramer's rule is what you'd want to use here. So 2 here can be rearranged so that I1 comes first. So if we did that, we're going to have minus I1 and then plus 1 minus J I2 is equals to 0. So now I just rearranged so that I start with I1. Everything else is supposed to stay the same. The target or the goal here is to find I1, I2, and I3. But first, we need to find the determinants. So we start with the main determinant. So we'll get the coefficients here. The coefficients, we see that here we have 1 plus j. Here we have -1. Here we have -1. Here we have 1 minus j. So the first determinant we'll get will be for 1 plus j. This is one set. Then here we have minus 1. Next, down here we have minus 1. Then here we have 1 minus j. Also, that is one set. So in trying to get the determinant here, we know we multiply these two. Minus, then multiply the minor diagonal. 1 and 1, they're both negative, so we get a positive 1. When you simplify that, we see that we just first have to distribute this or expand. So being a difference of two squares here, we just have to square 1, which gives us 1, minus square j, and j squared. Remember, j squared is the same as root negative 1 squared. And root of negative 1, when it is squared, it gives us negative 1, which ensures that this will have a plus on the middle. But don't forget, this is just this part, but it also has the minus 1 outside. So this is just 1 plus 1 minus 1, which is equals to 1. So D there has come out as a 1. Yeah? Yes? Are we okay?
Yes, sir.
Okay. So next, let's get dx. Or we can say dx, or we can say d1. So what are we doing here? Here, we'll get what comes after the equal sign. In equation 1, after the equal sign, we have 1. In equation 2, after the equal sign, we have 0. So those two, we'll now get this expression, and we'll replace in the first column. So we'll swap the first column. So the first column that is here, we'll swap that with a 1 and a 0. And we'll try to get the answer when it is now in this form. So what will be the determinant this time? 1 will multiply here, then this will multiply there. So that will just be a 0. So in this case, this reduces to just 1 minus j. This is d1. In the same way, to get d2, similar, but now it's this column that we'll swap. And we'll swap it with 1 and 0. Was 1 and 0? Yes, it was. When you try to get the determinant this time, this is the one that will give us a 0. So that now this and this to be 0 minus this and this will give us negative 1. So make this a positive 1. So that finally I1 will be dx or d1 over the original one. Are we okay up to here? Is this fine?
Yeah, yeah.
Okay. So what was our d1? Our d1 was 1 minus j. And our d, we got 1. So this is just 1 minus j. After getting this, we can even convert it to polar form. Currently it is rectangular. We know to say from here x is equal to 1. Y would have to be equals to, since this is a minus, y would have to be equals to -1. So based on this, we can get I in first magnitude first. For the magnitude, we have R is equals to x squared plus y squared. So this will be x is 1 plus -1 squared. Basically, this is just root 2. What are we getting here?
I know it's 1.41. This angle -45.
Okay, the angle will be, the angle will be what?
-45.
Yes, -45. So we've seen that I1 will be equal to 1.414, and then the angle, as you said, yes, this is -45 degrees. Since this is a current, we'll give it the amps. In the same way, we get I2. I2, it will be D2 over D. What did we get as our D2? D2, we got 1. So this is going to be 1 here over D. D was also 1. So here we're getting D2 as just 1 amp. Now D2, I2 there as 1. So here, regardless of how we look at it, polar or rectangular, still, even in polar, it would still be 1 phase 0. Meaning here, we can actually look at this one as just 1 as the peak value, phase angle 0 degrees. I went with the Celsius degrees. It is a current, so that will be the amps. From these two, we can get the steady state currents. From I1, for example, we can get the steady state current I1. We need the peak. The peak is 1.414. Then cos the angular frequency. The problem, what was the angular frequency? So when you check,
Was
1,000, right?
1,000, yes.
Yes. Then plus, now we need the phase angle. So this is for I1, phase angle comes from here. We got -45. The negative will make this a minus here. Then we have the 45 here. Oops. The same way, we can get the steady state current IT. Peak value comes from here. Angular frequency, same source, so still 1000. What did I write? So this is cos 1000 T plus phase shift. Here the phase shift came out as 0. So you can say plus 0. But basically there is no need for us to include this 0. So you might as well present this as 1 cos 1000 T as the current in the second mesh.